how all of our electronics work. It's a really elegant and powerful principle called Kirchhoff's current law. And, understanding it is kind of key to understanding the modern world. So let's get right into it.
So think about this for a second. In a really basic circuit, current just flows in a nice, neat loop. Easy enough. But almost everything we use is built on super complex circuits with just countless branches. So when that electrical path splits, what actually happens to the current? Does it get lost? Does it get weaker? This is the core puzzle we're going to solve today.
To get to the answer, we actually have to hop back to the 19th century. And trust me, this isn't just some dry rule from a textbook. Nope, it's a discovery with a fascinating origin story, all thanks to a brilliant mind that would pretty much change the course of physics.
So meet Gustav Kirchhoff. And what's really remarkable here is that he wasn't some old, seasoned professor when he had this breakthrough. No way. He was a university student back in 1845. He came up with this foundational law, a principle we still rely on every single day, while he was still studying. I mean, how incredible is that?
So, what was this big revolutionary idea? Well, at its heart, Kirchhoff's discovery wasn't really about inventing something totally new. It was about observing and putting a name to a fundamental truth of nature, the law of conservation. He basically realized that in an electrical circuit, nothing is ever really lost. And here it is. Kirchhoff's current law, or as you'll often see it, KCL. All it says is that at any junction point in a circuit, you can think of it as an intersection, the total amount of current flowing in has to equal the total amount of current flowing out. It means the circuit doesn't just use up or lose electrical charge at these points. It's a perfect, elegant balance.
Okay, I know that might sound a little abstract, but it's based on a really core principle in physics, the conservation of charge. And to make it super intuitive, let's use the perfect analogy.
Okay, so just picture a whole system of water pipes, right? The flow of the water, well, that's our electric current. And a spot where a bunch of pipes meet up, that's our junction, or our node. The whole plumbing system itself is basically the circuit. See, it's a really simple comparison that just makes the concept click.
And this phrase just sums up the whole idea perfectly. It's common sense, right? If you have 10 gallons of water flowing into a pipe junction every minute, you're going to have a total of 10 gallons flowing out through the other pipes. The water doesn't just vanish inside the pipes, and it's the exact same for electric charge in a wire.
All right, so the theory makes sense, and the water pipe analogy really helps, right? But now let's see how this law gives us real practical answers. We're going to put KCL to work with a simple example and see how it lets us figure out the missing pieces in a circuit.
So here's our scenario. We've got a node, a meeting point for 3 different wires. We know how much current is coming in from 2 of them, but we have no idea how much is flowing out of that third one.
Okay, let's walk through this step by step. First, we find our node, that central point. Second, we see we have 5 amps and 3 amps flowing in. The current flowing out is our big question mark. Let's call it X. Now we just apply KCL. Everything going in has to equal everything going out. So the math here is, well, it's about as simple as it gets. It's just 5 plus 3 equals X.
And boom, there's our answer. The unknown current flowing out of that junction has to be 8 amps. It's that simple and honestly that beautiful. No complicated math, just basic addition, all thanks to Kirchhoff's law. So maybe you're thinking, cool, that's a neat trick for solving homework problems. But it is so much bigger than that. This one simple rule is like a silent, invisible pillar holding up our entire technological world. Let's look at the huge picture here.
I mean, this rule is working right now inside the very device you're using to watch this. It's absolutely essential for designing the tiny microchips in your phone and for managing the massive power grids that keep our lights on. It's the absolute bedrock of modern electronics, and it ensures that everything we build works reliably and, more importantly, safely.
So just think about that for a second. The scale is mind-boggling. An observation made by a student almost 2 centuries ago is now being applied everywhere, from the tiniest nanometer-sized traces on a silicon chip you can't even see, all the way up to massive power grids that span entire continents. This one simple rule holds true and keeps our whole world running.
And that kind of leaves us with a really fascinating thought. KCL is a beautifully simple rule that governs unbelievably complex systems. It just makes you wonder, right? What other fundamental, elegant truths are still out there, hiding just beneath the surface, waiting to be discovered?